Welcome to UGC lecture series BSc Physics Honors Semester 6 Statistical Physics Lecture 10. In this lecture, we are going to discuss about Bose-Einstein Statistics, Bose-Einstein distribution law, degeneracy of a system, then summary about all these concepts. Bose-Einstein Statistics. We know in statistical physics there are two kinds of statistics: classical statistics, quantum mechanical statistics. This Bose-Einstein statistics comes under the quantum mechanical statistics, and this statistics is obeyed by identical and indistinguishable particles. Particles of integral spin like bosons will be obeyed by this Bose-Einstein statistics, and particles of integral spin having symmetrical wave function will also obey this Bose-Einstein statistics. This statistics got its name by Bose because he proposed the number of particles or entities in a energy level. This is what statistics deals. So, Bose-Einstein statistics says how many number of particles or atoms can exist in a particular energy level. This is a quantum statistics. This statistics will be obeyed by identical indistinguishable particles, and particles having integral spin will obey this Bose-Einstein statistics. Example for particles having integral spin is bosons. Actually, Bose utilized Plancks hypothesis of quantum mechanics, quantum theory, to propose this statistics. According to Plancks hypothesis, the radiation in a temperature enclosure, that is a thermal radiation in an enclosure, is composed of light quanta or particles having energy h nu. You know, according to Planck's hypothesis, particles coming out from a black body possesses energy h nu, where nu is the frequency of the quantum, and these quantum or light quanta are all not stable particles or stable entities. They are all dynamical entities. These dynamical entities possess mass of h nu by c square and momentum h nu by c. So, any entity or any particle, any body which possesses momentum means it is a moving particle or moving entity. So, the light quanta has got dynamical mass of h nu by c square and momentum h nu by c, where c is the speed of light. Then this light quanta is also indistinguishable. So, Bose utilized this concept to propose the statistics, that is number of particles in a particular energy level. Number of light here, the number of light quanta is not necessarily unchangeable, unlike in classical statistics where the number of particles is considered to be fixed. So, in classical statistics, number of particles should be fixed. In quantum mechanics or in quantum statistics, this concept need not be obeyed. So, Bose-Einstein statistics comes under quantum statistics. Next, according to the principle of conservation of energy in the emission process in the sense in black body radiation emission process, a new light quantum is formed, and if a quantum of frequency nu is absorbed by the walls of the enclosure, then it can be replaced by the emission of several quanta of frequency nu 1, nu 2, etc. So, emitted frequency nu is equal to nu 1 plus nu 2, nu 3, etc. Several emission of several quanta. So, this nu 1, nu 2, nu 3 are all emitted, then this nu is the absorbed one. So, according to the here the principle of conservation of energy is used. So, h nu is equal to h nu 1 plus h nu 2 plus h nu 3 etc. Here this h nu 1, h nu 2 are all energies possessed by each light quanta emitted. This h nu is the energy absorbed by the particles in the walls of a thermal enclosure. So, according to quantum hypothesis or Plancks hypothesis, h nu is equal to h nu 1 plus h nu 2 plus etc. Nu is equal to nu 1 plus nu 2 plus etc. In classical statistics, where the number of possible microscopic states of a system can be infinite, so the phase space of the system could be divided into an infinite number of cells of constant energy. So, phase space is a momentum position coordinate system. This phase space of the system can be divided into an infinite number of cells of constant energy in classical statistics, but in quantum statistics only a certain definite values of energy is permitted. Definite values of energy permitted. So, the number of possible microscopic states of a system is finite in quantum statistics, but it is infinite in classical statistics. So, BoseEinstein Statistics is obeyed very well by the experimental result. The phase space is divided into infinite elementary regions of constant energy. This is how that BoseEinstein Statistics paved a basic way to understand the distribution of atoms or particles in a particular energy level. This is the introduction about BoseEinstein Statistics. Now, let us come to the BoseEinstein distribution law. Mathematically, you can derive the BoseEinstein distribution law, which says that number of particles in a particular energy level. So, consider a system. You can imagine even a thermal system. That thermal system have n indistinguishable particles. Let these indistinguishable particles be divided into quantum levels such that there are n1, n2 etc. ni be the number of particles in groups whose approximate constant energies are epsilon 1, epsilon 2 etc. epsilon n. So, to derive BoseEinstein distribution law, we need to imagine a thermal system of n indistinguishable particles. Then these particles be divided into quantum levels named n1, n2, ni. Then energy of these quantum levels are epsilon 1, epsilon 2, epsilon n. Let Gi be the number of eigenstates of the ith level. Here eigenstate says the degeneracy or statistical weight of an energy level. Degeneracy means how many number of splitting can be possible with that energy level. That is the meaning of degeneracy. So, here Gi be the number of eigenstates or degeneracies of the ith level. If the energy level is non-degenerate, so that Gi can have 1 as value. Now, BoseEinstein's distribution gives the distribution of ni indistinguishable particles in Gi eigenstates or sublevels. So, particles are indistinguishable from each other. So, there is no distinction in choosing ni particles. That means, if you choose any number of particles, all the particles will be an identical one. That is what the statement says. Particles are indistinguishable from each other. So, there is no distinction in choosing ni particles. Now, each eigenstate of ith quantum state may contain the values 0, 1, 2 etc. up to ni identical particles. So, the next assumption here is each quantum state or each eigenstate contains how many number of identical particles. There may be no particles, only one identical particle can exist, two till that up to ni identical particles are possible in each ith quantum state. Now, sum of the energy of all the particles is different quantum groups constitute the total energy of the system. So, total energy of the system is obtained by adding all the energies of each particle. These are all the basic assumptions we need to make to derive the Bose-Einstein distribution law. Now, to find Bose-Einstein distribution law, two assumptions are made. First, a box is assumed. That box is divided into GI sections. Then Ni indistinguishable particles are to be distributed among these GI sections. So, assume a box. That box can be cuboid or cube. It can be on any shape. That box is divided into GI sections. Then number of particles filled in that GI sections are Ni. The choice that which of the section had to come first, that means the choice that which of the section head the sequence and be made in G1 ways, GI ways. So, the total number of possible ways in which Ni particles can be distributed in this section is Gi into Ni plus Gi minus 1 factorial. So, probability of distribution comes into picture here. This equation gives the total number of ways in which Ni particles can be distributed in GI sections. Because to derive Bose-Einstein distribution law, we assumed a cubical box or simply a box. That box is divided into GI sections. In that GI sections, Ni indistinguishable particles are to be divided. These Ni indistinguishable particles can be distributed according to this factorial equation. Now, these particles are indistinguishable. So, the permutations of particles among themselves will not give to indistinguishable arrangement. So, all permutations will be of same arrangement because the particles are same. So, the permutations among themselves also will give the same arrangement. Now, there are Ni factorial permutations, hence this equation, that is Gi into Ni plus Gi minus 1 factorial must be divided by Ni factorial. If we divide so, we will get the Gi Ni plus Gi minus 1 by Ni factorial alone. The reason for the division of the equation 1 by Gi is given here. A further distribution raised by more permutations of section among themselves do not produce different states. So, the further distribution raised by more permutations do not produce different states. So, that Gi such permutations should be made. So, the equation 1 must be again divided by Gi. So, the final result is this one. Thus, the required number of ways in which Ni particles are to be distributed among Gi sublevels of the ith quantum group is given by this equation Gi into Ni plus Gi minus 1 factorial over Ni factorial into Gi factorial. This equation can be further simplified as this one. Here the numerator Gi is missing. The denominator Gi factorial has become Gi minus 1 factorial. The reason for this one is that Gi is as it is. This Gi factorial can be expanded as Gi into Gi minus 1 factorial. So, that Gi and Gi got cancelled. So, you got the equation Ni plus Gi minus 1 factorial over Ni factorial into Gi minus 1 factorial. This is the number of ways in which Ni particles are distributed among Gi sublevels of the ith quantum group. Like that, you can find different equations for each quantum group. This result is in agreement with the postulate of equal of a priori probability, which states that the number of eigenstates for a given energy Ni is equal to the degeneracy Hi for Ni is equal to 1. So, similar expression can be found for various other quantum states. Considering all the available quantum groups with Ni particles in first group of energy epsilon, N2 particles in second group of energy epsilon 2 and N3 particles in third group of energy epsilon 3 and so on, the total number of distinguishable arrangement is given by G is equal to N1 plus G1 minus 1 factorial over N1 factorial into Gi minus 1 factorial. This has come by replacing the I by 1. In this equation, we got Ni plus Gi minus 1 by Ni factorial into Gi minus 1 factorial. Here we are assuming the number of ways in which N1 particles are to be distributed among G1 sublevels of the ith group. So, we got this equation. Then again N2 particles, arrangement of N2 particles in G2 sublevels of the second state can be done in this way: N2 plus G2 minus 1 factorial by N2 factorial into G2 minus 1 factorial into N3 plus G3 minus 1 factorial over N3 factorial G3 minus 1 factorial. So, summing up all these things, you will get the equation G is equal to sigma I Ni plus Gi minus 1 factorial over Ni factorial into Gi minus 1 factorial. Keep this as equation 2a. Here this Ni and Gi are large numbers, so we may neglect 1 in above expression. Therefore, this equation may be written as summation over I Ni plus Gi minus 1 over Ni factorial into G factorial. So, this Ni and Gi are not large numbers. So, you can this equation can be written like this. In accordance with the postulate of equality of probability of states, the probability omega of the system for occurring with the specified distribution is proportional to the total number of eigenstates. The total number of eigenstates is given here. Eigenstates in the sense energy level, total number of energy level. Eigenfunction means energy function. Eigenvalue means energy value. So, here eigenstates, energy states. So, the total number of energy states is given mathematically like this. Here this is the probability is proportional to total number of eigenstates. So, probability omega is equal to summation over I Ni plus Gi minus 1 factorial over Ni factorial into Gi factorial. Keep this as equation 3. So, by this equation we got the mathematical expression for the probability of a system with specified number of particles. That specified number of particles is proportional to number of eigenstates. Now, the distribution law of BoseEinstein statistics is obtained by determining the most probable distribution as in classical statistics. So far we have followed the quantum mechanics. At this step we need to derive the most probable distribution as we have done in the classical statistics. To do so, we have to take logarithm of equation 2. Equation 2 is this one. So, if you take logarithm, we will get log omega is equal to log of summation over I n I plus g I minus 1 factorial over n I factorial into g I minus 1 factorial into a constant. A constant should come here, so that this equation will be validated for all experimental results, which is equal to, this summation is taken out, summation over I log of ni plus gi minus 1 factorial. This ni factorial is in the denominator, so it can be written as minus log ni factorial, then another gi minus 1 is in the denominator as multiplication. So, minus log of gi factorial plus a constant. So, this equation is expanded like this. Here this ni and gi are very large numbers. Again we can use Stirling's approximation, where Stirling's approximation says log of ni factorial is equal to n log n minus n. Log of ni factorial is equal to n of log n minus n. By using this Stirling's approximation, we get log of omega is equal to summation over I ni plus gi into log of ni plus gi minus ni into log of ni minus gi log gi plus constant. Keep this as equation 5, remembering that this gi is not subject to variation and gi varies continuously. The differentiation of above equation gives, this is the equation. If you differentiate this, you will get delta of log omega is equal to summation over I n I plus g I into 1 by n I plus g I into del n I plus log of n I plus g I into del n I minus n I into 1 by n I del n I minus log of n I del n I. Here this del sign comes to denote the variation in all the quantities. After simplifying this expression, we get del log omega, that is differentiation of log omega, is equal to summation over I log of n I plus g I minus log n I into del n I. So, summation over I log of n I over n I plus g I del n I. This is the number of ways that g varies, number of ways that g varies. To get the most probable distribution, that probability should be maximum. So, that del log omega maximum must be equal to 0. You know, any differentiation, any constant is differentiated, it will give a value of 0. Thus, the condition of most probable distribution gives summation over I log of ni over ni plus gi into del ni is equal to 0. Keep this as equation 7. Based on this, two subsidiary conditions are obtained. They are total number of particles of a system is constant, that is equationally it can be written as n is equal to summation over I n I is equal to constant. This gives the total number of particles of a system. Then del n is equal to summation over I del n I is equal to 1. So, the total energy of the system is constant, that is E is equal to E I n I epsilon I is equal to constant. Then del E is equal to variation of this E with respect to any variable is equal to summation over I epsilon I del n I is equal to 0. Epsilon I del n I is equal to 0. Keep this as equation 9. Now, apply the Lagrangian method of undetermined multiplier. To apply this, we multiply equation 8. This is equation 8, that is n is equal to summation over I n I is equal to constant. we multiply equation 8 by alpha, equation 9 by beta, and adding the result we get result experiences to equation 7, so that we get summation over I log of ni by n plus ni plus gi plus alpha plus beta epsilon I into del ni is equal to 0. Keep this as equation 10. As the variation del ni are independent of each other, we get this log of ni by ni plus gi plus alpha plus beta epsilon I is equal to 0. Therefore, this you got ni by ni plus gi is equal to e power minus alpha plus beta epsilon I. Take this alpha plus beta epsilon I that side, so it will become minus alpha minus beta epsilon I. So both the sides, this side you got the left hand side of this equation you got logarithm, that side you don't have. Take antilog on both sides or exponentiate both sides. The left hand side logarithm gets cancelled, right hand side component is exponented, so you got this expression ni by ni plus gi is equal to e power or exponential of minus of alpha plus beta epsilon. Now this is in the exponential area you got a negative sign, so both sides can be inverted. You will get ni by ni plus gi is equal to e power alpha plus beta epsilon. So 1 plus gi by ni is equal to e power alpha plus beta epsilon I. So gi by ni is equal to e power alpha plus beta epsilon into epsilon I minus 1. Keep this as equation 11. This equation represents the most probable distribution of the particle among various energy levels for a system obeying Bose-Einstein statistics, and this is known as Bose-Einstein distribution law. Degeneracy of that state. Degeneracy is a concept which explains the number of states, number of splittings an energy level can do. So in some cases there is only one eigenfunction corresponding to each eigenvalue. In such cases, that energy state, eigenstate level is said to be non-degenerate. In some cases, if the energy eigenstate is degenerate, then there will be number of eigenfunction corresponding to a single eigenvalue. So in these cases, the eigenstate is said to be degenerate. This is how degeneracy of a state can be defined, and this degeneracy concept is used in explaining the splitting of spectral lines when the spectral lines are passed through a magnetic field, electric field, or any external field. If a spectral line is passed through any external field, it will split. This splitting is called degeneracy. The reason for the splitting is the quantum state of the energy level. So here in statistical mechanics, this degeneracy says the number of possible splitting of an energy level. Number of possible splitting of an energy level. In the degenerate case, the number of eigenstates for the particular energy state or energy level is called degeneracy of that state. Thus, if gi is the degeneracy for the eigenvalue epsilon I, then gi is the number of eigenstates. Then for a non-degenerate case, that gi is equal to 1. Bose-Einstein statistics is obeyed by identical indistinguishable particles having integral spin bosons. So bosons will obey Bose-Einstein statistics. Bose-Einstein distribution law gives the distribution of Ni particles in Gi energy states as Ni is equal to Gi by e power alpha plus beta epsilon I minus 1 is the formula used to calculate the distribution of particles, Ni particles in Gi energy level. Then if there are number of eigenfunctions for single eigenvalue, then it is said as a degenerate state. So, degeneracy, there is no degeneracy means that Gi is equal to 1. These are all the concepts you learnt in this lecture. After listening to this lecture, you can answer the following questions. What is known as phase space? Give examples for bosons and state BoseEinstein statistics. What is called degeneracy of an energy state? Thank you.